All right, guys, I'm going to try to do a review of chapter 15 in just a few minutes. So this is the first half. All right, so chapter 15 we did before we left. It's going to be a little bit of a challenge here, but we're going to get through it. All right, so electric fields and forces. So if you remember, we started with Walter Lewin and his MIT lectures. And so we started talking about how the Greeks really first started noticing electricity. And they found out that when they rubbed amber, that it attracted straw. And so we kind of just played with it until then. Benjamin Franklin was really the guy who um, really, very much um, made modern electricity kind of what it is now. He was also the guy who mislabeled positive and negative um, backwards. So we're stuck with it. So there are two kinds of charges, positive and negative. And then this right here, oh gosh, here we go. Like charges repel and unlike charges attract. That would be called the law of charges. Okay, and as you know, as we get on, it gets much harder and much more important. So we find positive charge in an atom in a proton. The negative charge is the electron. We've also talked about how electrons are the only thing that moves. So you can never change a positive charge. You can only add or take away a negative charge. Charge is conserved, so it's along with momentum and mass and all those other things. It must go somewhere, so you have to always know where it goes. And then we talked about how charge is quantized, so it comes in packets of charge. Okay, this right here is the charge of a proton. It's also the charge of an electron. You just have to change the sign. Okay. And we talked about the formula because it's not really in your book anywhere. Q, oh my gosh, equals Ne, where Q is the charge of the object, N is the number of electrons, and E is the charge of an electron, that negative 1.6 times 10 to the negative 19. Okay, so we did those. We did a couple problems like that. Those are pretty easy. And it's also baffling to understand how many electrons are actually moving. Then we have the difference between conductors and insulators. Conductors are things where electrons are not held very tightly, that the electrons can move easily. Commonly, most metals are. Specific aluminum, copper, silver, and gold are the best conductors we have. And then insulators are things that hold on to charge or hold on to their electrons much more tightly. Glass, rubber, most of the nonmetals, it's harder to get a charge. And then there's that semiconductors, those things that show up on that stair-step line on the periodic table, and they can both be conductor or insulator depending, usually on temperature. And silicon and germanium are the two famous ones that we use for circuit boards. All right, then we went through charging by conduction. So this is where you take a charged object. So this one is a negatively charged rod, and you bring it near a not charged object. And what happens is it polarizes, right? So the positive charges are attracted to the negative. Okay, when I make contact, what ends up jumping is the electrons. So then what ends up happening is I have a net negative charge on the object. Oops, sorry. And then we have charging by induction. So this way there's no actual contact. Okay, so this is again polarization. And we kind of talked about this a second ago. So I'm bringing a negative object next to a neutral object. Okay, and what's happening is the negative charges are being pushed to one side. If I then take and ground this object that I polarized, okay, the negative charges will march away. So in the end, I will end up with something that is positive. Okay. And if you notice, the positives will redistribute throughout the whole object because they want to be away from each other. Okay, like charges repel. All right, so we went through that. Polarization, so that we talked about that. That's when you have a no net charge on the object, but one side of the object will be positive, one side will be negative, and you talk about that a lot in chemistry, like with the water molecule, where one side is positive and one side is negative. This would be an example of that with a balloon. So here we have a balloon that was positively charged, probably by rubbing it against a shirt or something, brought up next to a wall. And what ends up happening is the charge in the wall is induced, or the wall becomes polarized, and that's how the balloon sticks. And then we get to Coulomb. Cool guy. He has a law named after him. Okay, it's an inverse square law. It's very, very similar to the law, Newton's law of gravity, except this time we're talking about charge. If you notice here, in his equation, we use the absolute value of the two charges because you need to figure out direction based on their charge and the situation. Okay, so we have Coulomb's law. Force, electric force, is equal to Coulomb's constant times the charges of each of the objects divided by the distance they are squared. Coulomb's constant, we used 9 times 10 to the 9th because it's just easier and no more unexact. Most of the time you'll be working in microcoulombs, and if you remember, micro is 10 to the negative 6. Okay, nano 10 to the negative 9, pico 10 to the negative 12. Force is a vector, so again, you need to figure out direction. And that formula only works for spherical objects or point charges. Okay, so there's your charges and masses, just in case you need them for problems. So again, here I have an example where we have two positive charges. They will try to be getting away from each other. If you notice, the force on one because of 2 and the force of 2 on 2 because of 1, they're the same, just in opposite directions. Okay, if I have two charges that are equal in magnitude but in opposite charges, the forces will become together because they're attracted. Okay, so the forces are equal but towards each other. Okay, so the forces that are created are field forces because it's sort of like gravity. So the influence of a charge technically goes on forever. They're also called action at a distance forces. And if you think about how we do gravity, electric force is a lot like that. And here's the comparison between the two, between gravity and electrical force. They're both inverse squares. In gravity, or the gravitational constant, you have capital G. In Coulomb's law, you have K. Electrical forces can be either attractive or repulsive, but gravity is always attractive. Okay, that right there is the key difference between the two. Also, electrostatic force is extremely strong compared to gravitational force. That very weak gravitational force, even though it matters a lot to us, in the grand scheme of things in the universe, it is super weak, and we can't seem to figure out how it fits in with everything. Okay. Then we have the superposition principle. So this is where you're starting to add charges together. So this would be Coulombic love triangles, if you remember that worksheet. So you always have to add all the parts as vectors. So you're breaking the pieces of the forces into their components. See how we broke that into its components, and that way we can add them all together in the chart that we always use. Okay. Those are the problems we can do for 15.3, or that we did. If you want me to redo any of them, leave me a message and I will. Just make sure you put the section and the number. Electric field. So then we moved on to field, which was capital E. Faraday was really the guy who figured this out. So electrical field is sort of like gravitational field. It's the region around the object that the charge actually creates a force. Okay, so if I have a large object with a lot of charge here and I bring a positive test charge, and we always for some reason have positive test charges, what's going to happen is this electric field is going to push it out, okay? The formula for electric field, if you notice here, we got a couple versions. We got capital E, it's a vector, is equal to field over charge, force over charge, wow. And then what they did here was they just substituted in Coulomb's law for it to solve it easily. So K is Coulomb's constant, 9 times 10 to the 9th. Q would be the charge on a large object and divided by the radius squared, okay? The units of field are newtons per coulomb, okay? Again, it's a vector, so you have to figure out direction based on the charges of the objects. And for some reason, we always use positive test charges, okay? So if I brought a positive test charge near this negative thing, it would be pulled towards it because opposite charges attract. However, if I brought a positive test charge next to a large positive object, it would be repelled. Okay, so it would go away. All right, that's the end of the first half of chapter 15. Check back with you in a few minutes.